Okay, thank you. My name's Jason West. I'll be presenting on intraseasonal variability in the atmosphere and oceans. And first, I'd like to just thank the AGU and NASA staff for having me here. I'm really humbled to be presenting on the Hyperwall. And I hope I can explain something about intraseasonal variability in 10 minutes. We'll see. So for those who are not familiar, intraseasonal variability refers to processes roughly on timescales of 20 to 90 days. So it's kind of a weird timescale in between weather and climate, but it affects a lot of other processes in the atmosphere and ocean climate system. So the first animation I'm showing is the northern hemisphere summer manifestation of intraseasonal variability. It's called the Monsoon intraseasonal oscillation. As the name implies, and as you can probably see from the animation, it's very closely tied to the Indian summer monsoon. But as opposed to being like a synoptic weather timescale manifestation of that, it's a 30 to 50 day timescale process. So what I'm showing here are, in alternating green and brown colors, are essentially rainfall anomalies associated with the monsoon intraseasonal oscillation. And these come from outgoing long-wave radiation data, which is commonly used as a proxy for rainfall in the tropics. And I'm also showing in the arrows, those are the surface wind vectors. The OLR anomaly data come from polar orbiting infrared radiometers, and the wind data come from scatterometers, also satellite mounted. And what you'll notice here are alternating conditions of wet and dry on roughly 30 to 50 day timescales. That's what the day counter is counting off, and it's cycling again and again. The way I constructed this animation was I used 12 years of satellite data for both the OLR and the surface wind data. And I constructed 8 what are known as phase composites. For those of you not in the intraseasonal field, they use EOF-based indices to group the MISO, which is the monsoon intraseasonal oscillation, into one of 8 phases, which represents its position on any given day. So I took the 12-year satellite data set and generated 8 composites, one for each phase, based on the Maddened Julian oscillation index, which I obtained from the Australian Bureau of Meteorology. And that's been done many times in the literature. It's a very effective way of visualizing the monsoon intraseasonal oscillation and the Maddened Julian oscillation, which I'll show in a couple of slides. What I hope to add into this is the appearance of fluid motion. So the way I accomplished that is I took the 8 phase composites and temporally interpolated to approximately 600 image frames. And when those are displayed at 30 frames per second, it gives the appearance of smooth motion, which is maybe closer to what you would see in nature. So that's what I hope to accomplish with this animation. So this is the same process, the monsoon intraseasonal oscillation, but I'm using 2 different data sets here. I kept the green and the brown colors consistent with the previous animation. They also represent rainfall anomalies associated with the MISO, only this time they come from the TRIM satellite, specifically the microwave imager that was mounted on TRIM. And I'm using the entire 17-year data set from TRIM to generate those anomalies. And what you'll notice is you see finer scale features in the rainfall anomalies, and that's because TRIM data are available at a quarter degree, whereas the previous animation only included 1 degree resolution data. And in addition to the rainfall anomalies, what I really wanted to show with this animation was the connection between the atmosphere and the ocean. So I'm also showing in red and blue sea surface temperature anomalies. Those also come from the microwave imager on TRIM. And what I wanted to show here was what's known as the quadrature relationship between rainfall and sea surface temperature. You'll notice if you watch the rainfall and the sea surface temperature anomalies, you'll notice that they're out of phase by a quarter cycle. And that's because it's essentially the solar shortwave radiative flux that is the dominant process that affects the interplay between the atmosphere and ocean. So you notice that the positive rainfall anomalies lag behind warm sea surface temperature anomalies and are themselves lagged by cool sea surface temperature anomalies. And that makes intuitive sense. As the ocean surface warms, it increases the heat flux to the lower atmosphere that destabilizes it, which generates convection and rainfall. The appearance of deep convective clouds reduces the solar shortwave radiative flux, which goes into the ocean, which then cools the surface, and the process repeats again and again. So again, this is a well-known relationship, but what I really wanted to convey here was an intuitive sense for what that really looks like. So the next two animations I'm going to show are using the exact same data sets as the first two animations, except now I'm switching seasons to Northern Hemisphere winter. And in the Northern Hemisphere winter, the dominant mode of intraseasonal variability is known as the Maddened Julian oscillation. It's similar to the Monsoon intraseasonal oscillation, except now you'll notice that the direction of propagation is eastward instead of northward. The variability, or the convective cells, are also much larger and of higher magnitude on average than in northern summer. And I generated the same set of composite images again for the 17-year TRIM satellite data record. And I think the northern winter manifestation of this shows the out-of-phase relationship between rainfall and sea surface temperature much more clearly than the northern summer animation of it because of the larger scale. You can really see how the rainfall lags just behind the warm sea surface temperatures as they propagate eastward, and the rainfall, or the deep convection in the tropics, then cools the sea surface behind it, and the process repeats. So I guess that's a really brief introduction. I hope maybe I shared something about intraseasonal variability with all of you, maybe something about how I generated the animations. And I'd like to thank AGU and NASA again, and all of you for your attention.